So this is actually the last lecture on probability. Okay, and then we're going to move to a totally different topic. So, we're going to talk about something called expected value, which is something related to random variables. But expected value is very closely related to taking an average, which is something probably you've seen before. So just as a bit of a review, so the average or mean of n numbers, let's say x1, x2, up to xn, it's just what you get by adding up all the numbers and then dividing by n. So the notation I'll use is x with a bar on the top, and it's just x1 plus x2 plus dot 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 up to xn divided by n, right? Okay, so for an example, let's say you've got 100 people. Let's say they're being surveyed. About the number of pairs of shoes they own. Okay. And let's say that the data that you get is as follows. So okay, let's say X is the number of shoes that a given person owns, and then we're going to, each number has a certain frequency. Okay, so out of the 100 people, nobody has 0 pairs of shoes, I hope. So you survey 100 people, none of them said they have 0. 15 said they have 1 pair. 35 said 2. 30 said 3. 15 said 4. And let's say 5 people said they have 5 pairs. And let's just say nobody said they had more than 5 pairs. Right? So then the question is, what is the average number of pairs of shoes among the people in this sample? So in other words, among people in these 100 people. Okay, so, right, so we're just going to kind of apply this formula. You're going to have a whole bunch of numbers, add them up, divide by n. Can anyone see what I should divide by? Any other thoughts about it? Yeah. Yeah, 100. So I do see where you got 6, right? There's 6 possible kind of outcomes, like 0 up to 5. But I'm not asking the average like among all outcomes or something. We're really thinking we got the sample of all the 100 people and we want to say, on average, how many pairs of shoes do they own? So if you wanted to compute that average, what you would do is you would take, like imagine you're, taking this survey, you'd ask a person how many pairs, they'd say 3, you'd add 3 to your total, they would say 5, you add 5 to your total, they say 5, another person says 5, you add another 5, and then at the end you just divide the whole thing by 100, right? So yeah, we're going to want 100 on the bottom. On the top, on the top you need to kind of think of this as if like you're adding up all these different numbers. So you don't just add 0 plus 1 plus 2 plus 3 plus 4 plus 5, right? Because that wouldn't take into account the frequencies. So you had 15 people who said 1. So it's like in your 100 numbers, 15 of them are 1s, right? And in your 100 numbers, 35 of them are 2s, and so on and so forth. So on the top I've got 0 people who said 0. I've got 15 people who said 1. So it's like I've got 15 1s on this numerator, but I can just write that as 15 times 1. There are 35 people who said 2. Thirty people who said 3. 15 people who said 4. And 5 who said 5. Right? So note that like these numbers, these frequencies add up to 100, right? So yeah, you should be thinking of, among your 100 numbers, 30 of them are 3s, right? Any questions about that? Okay. And I think if you compute this, you end up with 2.6. Okay, so which means on average, a person in this group has about 2.6 pairs of shoes. Okay. This might seem weird to you, like if you're not used to this, right? What does it mean to have 2.6 pairs of shoes? That doesn't make sense. You can't have 2.6 pairs of shoes. What's 0.6 of a shoe? I don't know, maybe flip-flops or like 0.6 of a shoe or something, I don't know, but yeah, so like nobody can actually have 2.6 pairs of shoes, but when you're talking about an average, it doesn't need to be a whole number, right? It can be just 2.6. It's just an average, right? Okay. So this is how you compute an average. But what we really want to talk about is something called an expected value, which is really closely related to an average, but it's not quite the same thing. So to kind of introduce this, I want to kind of take this average and sort of analyze it in a slightly different way. And once I rewrite this in a different way, we'll see that this is actually some sort of an expected value of a random variable. So let me rewrite this by just sort of breaking up these terms and putting them all over that denominator. So I've got 0 times 0 over 100 plus 1 times 15 over 100 plus 2 times 35 over 100 plus 3 times 30 over 100 4 times 15 over 100, and then 5 times 5 over 100. Okay. So just to be clear, to solve this problem, you don't have to do this. Like, the answer is 2.6, but I'm just going to kind of rewrite this in a different way to give you a bit of intuition about what expected value means. So the way I've written this, if you think about it, suppose I pick a random person from this 100. What's the probability that that person has one pair of shoes? Yeah? Probably, if I could do that math in my head. Yeah, 15 over 100, which, yeah, it is 3 over 20. Right? Because, yeah, you got 15 people who said they have one pair of shoes, so it's going to be 15 over 100. And you can see I've got that number right here. If I picked a random person, the probability they have 2 pairs of shoes is 35 over 100, right? So all of these probabilities are kind of sitting here in this expression. So it turns out, so if I let x be the number of pairs of shoes of a random person within these 100 people. So random person from these 100, then this calculation can be rewritten as, so apologies, I'll write it over here because there's no space there. But it's 0 times the probability that x equals 0 plus 1 times the probability x equals 1, 2 times the probability x equals 2, 3 times the probability x equals 3, 4 times the probability x equals 4, and then 5 times the probability that x equals 5. So all I'm saying is that these fractions here, you can actually think of them all as probabilities, right? And I guess what I want to sort of say here is that this kind of formula here it's not a coincidence. So basically, like the average of these numbers, or the average number of shoes in this example, is equal to the expected value of this random variable, and where this would be e of x, which is the expected value of x. Okay. So generally speaking, the expected value of a random variable is computed by going through all the possible values, taking that value times the probability that x equals that value, and just adding it up over all possibilities. So that's how you compute an expected value. So it's very closely related to an average, but it's not quite the same thing. So let me now give you a proper definition of this. Let's let x be a random variable with n possible outcomes. let's call them little x1, x2, up to xn. Okay. The expected value of x is computed with the following formula. So first of all, the notation is e of x. Okay. And then we just go over all the possible values. So the first possible value is x1. We take x1 times the probability that x is equal to x1. Then we do x2 times the probability that x is equal to x2. And then we just go through all the possibilities. We have like xn times the probability that x is equal to xn. So you go through all the different possibilities and add these things up. Okay. So this is just a general, this is a general formula for the expected value. And hopefully you can see how this matches what we got in this example for the average, right? So average and expected value are kind of the same thing. The only small difference is that when I compute an average, basically I've already got my n numbers and I'm taking their average. Like it has to come from some kind of a, I don't know, a survey or a sample of some sort. There's a bit of a difference with an expected value because this x is more theoretical. Like you could just say, I'm rolling dice or something. Then you know that the probability that you get, if you roll the dice 10 times, the probability that you get 6 even numbers in those rolls is equal to some value. You don't actually have to do the experiment to find out the numbers, right? That's the only difference, but otherwise, it's the same thing. Okay. Let's do an example to see how to compute this. So let's say we roll 4 dice. Okay. And let's say that x is the number of ones rolled. Okay. And let's compute, or actually let's say more than that. So let's suppose the question asks to write the probability distribution of x and compute the expected value. Okay. So this random variable x, it's a special type of random variable that we talked about last time. Can anyone remember the name of that type of random variable? starts with a B. So it's a binomial random variable, right? Right, because X just depends on some independent trials of the same experiment over and over. You know, you just roll a die over and over or whatever. So it's a binomial random variable with 4 trials, so n is equal to 4. Success probability if we think of a success as being rolling a 1, then the success probability is p, which is 1 over 6, and failure probability q, which is 5 over 6. So does anyone remember the formula for the probability distribution? So let's say k is a number. K is like 0, 1, 2, 3, or 4. What's the probability x equals k? Yeah. Yeah, something like that. So yeah, you got the n choose k, p of the k, q of the n minus k. And then we can just like plug our numbers in here, right? Well, okay, I don't know what k is, but I know n is 4. So I got 4 choose k, 1 over 6 to the power k, and then 5 over 6 to the power of 4 minus k. Right? So I know this, like, you're probably not studying this yet because the quiz today is not on this, but at some point you're going to want to memorize this formula. It's quite useful. Okay, so then we can do our I mean this already is the probability distribution, but let's just write it in a table as well. Okay, so the probability x is equal to 0. We just plug in k equals 0, so we get 4 choose 0, p to the 0, q to the 4, 4 choose 1, p to the 1, q to the 3. If you don't know where these are coming from, they're coming from this plugging in different values of k. So then we've got 4 choose 2, p squared, q squared, 4 choose 3, p cubed, q to the 1, 4 choose 4, p to the 4, q to the 0. Oh, what was p and q? Sorry, I should have written my bad. So sorry, all those p's should have been 1 over 6. All the q's are 5 over 6. Okay. Okay, so finally, let's get the expected value. Okay. So to get the expected value, we're supposed to go through all the possible values for x, take that number, which is, so 0, 1, 2, 3, and 4, we take that number times the probability that x equals that number. So basically we just take 0 times this, plus 1 times this, 2 times this. We just multiply the thing in this column by the thing in that column. So it's 0 times probability x is 0 plus 1, probability x equals 1, plus 2 times probability x is 2. So 0 times 4 choose 0, 1 over 6 to the 0, 5 over 6 to the 4, plus 1 times 4 choose 1, 1 over 6 to the 1, 5 over 6 cubed, 2 times 4 choose 2, 1 over 6 squared, 5 over 6 squared. 3 times 4 choose 3, 1 over 6 cubed, 5 over 6 to the 1, and then we've got 4 times 4 choose 4, 1 over 6 to the 4, 5 over 6 to the 0. It's a lot of writing. If you plug in all the numbers in your calculator, you'll see that that gives you 2 over 3. Okay, so what this says is if you flip a coin 4 times, you should expect to get about 2 over 3 ones out of those 4 rolls. Right? Did I say flip a coin? Sorry, I mean roll a die 4 times, not flip a coin. Okay, any questions about any of that? Okay, so that calculation was long. It'd be nice if we had a better way to do it, and luckily we do. So this is something you need to remember because it's going to save you a lot of time. So here's a fact. If x is a binomial, random variable, with n trials and success probability p, then the expected value of x is just n times p. That's all. Okay. So if we knew that when we did this example, it would have made our lives a lot easier, right? Because we just realize, oh, so in the example, we just realize n is 4, the success probability is 1 over 6. If you reduce that fraction, you get 2 over 3. So it's really important to be able to look at a random variable and determine if it's binomial. Because if it is binomial, then some of these calculations get way, way easier. So you really can, if you're computing the expectation of a binomial, you can just determine what is n, what is p, and just multiply them, and you're done. So, and that's particularly important if you're, let's say you're rolling a die 3,000 times, and you want to know the average number of, or the expected number of 2s that you roll. Well, you're not going to want to compute the probability x equals 0, 1, 2, 3, 4, up to 3,000, and then do this ugly calculation. You just say, oh, 3,000 times 1 over 6, got it, right? It's like 500 or something. Okay. Any questions about that? Okay. Okay, so let's do an example which is not a binomial experiment. So let's say we draw 3 cards without replacement. And then let's let x be equal to the number of face cards drawn. Okay. And now we want to compute the expected value of x. Okay. Okay, so so this is not a binomial trial, right? Because we saw examples like this last time, right? So this is not binomial because the trials are not independent. Okay. Because if I get a face card the first time, I'm a bit less likely to get it the second time. So we can't really use our formula there. So we're going to need to do more work. So let's say, so let me draw my probability distribution. So these tables I'm drawing, these are probability distributions, right? This is okay. So a bit of a review of probability again. So if I pick 3 cards, oh, by the way, the number of face cards in a deck, right, is 12 because there's Jack, Queen, King, 4 suits, so 3 times 4. So you got 40 non-face cards. So what's the probability I get 0 face cards? So I'm picking 3. Or should I say I'm choosing 3? Yeah. Yeah, not getting a face card, yeah. Well, I'm not sure where the 9 comes from. Is that for picking a non-face? The thing is, they don't have to necessarily, so you could get 3 different 2s or something. So you don't have to pick different denominations. So it could be, it doesn't necessarily need to be different denominations. It's easier than what you're saying, basically. It's just going to be 40 choose 3 over 52 choose 3, right? The denominator is all the ways to pick 3 cards if you don't care about what order you pick them. The top is all the ways to choose 3 non-face cards, right? Okay, so then this one's going to be 12 choose 1, ways to choose 1 face card, 40 choose 2, ways to choose 2 non-face cards, and again divided by 52 choose 3, which is the total sample space of all possibilities. Then we've got 12 choose 2, 40 choose 1, or 52 choose 3. Then we've got 12 choose 3, 40 choose 0. Over 52 choose 3. Okay. Any questions about how I got these numbers? So this counting and probability stuff is hard. But we have done quite a few examples like this before. And it's always kind of the same type of answer. Okay, so to get my expected value, so I just go through all the different values. Basically I go through each line. I take 0 times this, plus 1 times this, 2 times this, 3 times this, right? And I just add them all up. So 0 times 40 choose 3, or 52 choose 3, plus 1 times 12 choose 1, 40 choose 2, or 52 choose 3, plus 2 times 12 choose 2, 40 choose 1, over 52 choose 3, plus 3 times 12 choose 2, over 52 choose 3. Okay. So is it clear where I'm getting these numbers? Like, this value here, for example, is the probability that x equals 2, right? So you take 2 times probability x equals 2, and et cetera, for all the different values of x. At the end, you get something like 0.69231, roughly. Yep. Yeah. Yep, yep. So on average, like you'd expect to get this many, which again is like not really a number of cards you can get because it's not a whole number. But basically, suppose I repeat this experiment like 1,000,000 times, right? I take 3 cards, I see is there a face card, or sorry, I count the number of face cards. I do this a million, or a zillion times, right? Then the number of times, sort of the average number of face cards I get on a round would be very, very close to this. So it is like the average number you would get, which is less than 1, but yeah. Any other questions? Yeah? Yeah. 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 Exactly. Yeah. So so just to repeat that louder for everybody, if it is random, if it's binomial, you can just say expected value equals n times p, and you're done, right? If it's not binomial, like in this case, then you're going to need to compute all of these different probabilities. You can do it in a table if you want. You don't have to write the table, but unless you're asked to. But I think it's a convenient thing to just write the table and then just go through this times this, this times this, this times this, and add them up. Yeah, but it's a good question. Or sometimes you'll have a question where you're given a table with probabilities already, and then you just have to do the multiplying and adding, you know. So you might not have to compute these values for every question, right? Okay, let's do a trickier question. So let's say a life insurance company is selling a policy, so life insurance policy that pays out $50,000 if the customer dies in the next year. Okay. And let's suppose that somehow this insurance company determines that, so they determine that this customer has a 0.06% chance of dying this year. Oh, sorry, I wanted to do 0.6, not 0.06. Okay. So now the question is, how much should they charge the customer so that they have an expected profit of $100? So how much should they charge to get an expected profit of $100. Okay. Okay. So this is kind of a tricky one because it's kind of backwards. It's telling you the expected value, the expected profit, and it wants you to determine another variable with respect to that. So let's say X is the profit for the company. Let's say C is the cost of the policy. So I'm going to write a probability distribution. So there's two outcomes, right? Either this person dies in the next year or they don't. There's only two possibilities. If they don't die, then what's the profit? Sorry? Well, the company will still profit because they're going to charge something for this policy. So yeah, we're not talking about the profit to the descendants of or the family of this person or something. We're talking about the profit to the insurance company. Yeah. Yeah, or in this case, I'll call it C because that's what we've written as the cost. But yeah, I think you've got the right idea. So, right. So if the cost of the policy is C, then if the person doesn't die, then the insurance company just keeps that money and they pay out nothing, right? They just get the cost. That happens with probability. So if there's a 0.6% of them die,